Hey everyone, welcome to another lecture in the DSA series by the ML Hub. So in the last lecture, we discussed about stacks, but in this lecture, we will be discussing about queues. So let's get started. So queue is another linear data structure, and no matter what is the implementation, either of stack or queue based on linked list or array, both will be linear. But just in case if you're implementing it using a linked list, in that case it won't be sequential. Alright, so queue is a linear data structure that follows a slightly different principle when it comes to addition and deletion of elements from this data structure, and this is called as FIFO, which stands for first in first out principle. Okay, the stack was first in last out, but the queue is first in first out. So imagine a scenario in which you are going to watch a movie, okay, and you want to buy the ticket. So you go to a ticket counter and see that there are already people which are present in the queue waiting for the ticket to get purchased. Okay, so you also go and stand in the queue, right? So you also go and stand at the end of the queue. But the person who will get the ticket first will be the one who joined the queue first, right? You are the last one to join the queue, but the person who will get the ticket first will be the one who joined that queue first. So this is what first in first out is. So the person who first entered the queue will be the person who first exit the queue. That's it. Okay, so this principle, when a data structure is implemented using this principle FIFO, it is known as a queue. Alright, so the analogy can be waiting line at a ticket counter. So in stack, we read about a parameter which is important when it comes to addition and deletion of elements, which is top of the stack, where exactly the index is of the last element which was added or the current topmost element, right? So in queue, we have two parameters. The first one is head, the second one is tail. So what exactly it is? So now a question can come up in your mind that why two parameters are required for implementing a queue. So let's have a scenario in which we are adding say 3 elements in a queue. Suppose it's an array of size 4, right? So there are two operations that can be performed in a queue: addition, which is insertion, and deletion, right? And these operations are called as Enqueue and Dequeue respectively. So we'll see it later exactly how we will be adding it. But if we are maintaining this queue, this is a queue which is in this direction. So this will be the inlet and this will be the exit of the queue. Or inlet or entry would be a better word. This will be entry. This will be the exit. Okay. What I meant by entry? So the elements that will enter in this queue will be from right hand side, and the ones who will take exit would be from left hand side. So if say let's assume you add 1 to this queue, okay, so the one we will put in the first index, right? Now you add one more element 2, so 2 will be there. Why? Because entry is from the right hand side, so we'll enter from the right hand side, and wherever the first empty place towards its left, we'll put the element. Now we have to enter 3. So 3 will be here, right? So now if we want to remove an element from this queue, so it will be the one which was added first, which is 1. So this will be deleted. So for both these operations to occur in constant time complexity, we need to maintain 2 pointers. The first, who is responsible to check that at what position the first element that I need to exit is present. In this case, if this is a queue, you can think of a pointer who is pointing towards the first person standing in the queue, and the tail is the pointer who is pointing towards the last person standing in the queue. Okay, so if I maintain 2 pointers, first pointing towards the head and second pointing towards the tail, let's call it H and T. If I maintain 2 pointers, then both insertion and deletion can occur in constant time complexity big O of 1. Correct? So that's why 2 pointers are required to efficiently implement the queue data structure. Okay, so now the definition of head and tail. So again, the definition varies from textbook to textbooks. Some textbooks refer as head, which says the position of the front element. In this instance, the element which is present in the front is 15. So head is the index of the first element which is present in the queue, or you can also say the index of the element which will exit the queue if a deletion operation is applied on it. And tail is the position where the next element will be inserted. Okay, so the position in this case, if I want to insert an element in this queue, it is towards the right hand side of the last element, which is 4. Okay, so the index where I will insert is 12. So this is what tail is. But in some textbooks you will find that tail is the index of the last element in the queue. So it can be 11 as well according to like some textbooks. But in both the cases, the overall idea remains the same. You will add the element towards right whenever a new element will be entered in this queue, and you will remove the element from left. Okay, from head the deletion will be there, and towards its tail you will add or enqueue the elements in the queue. Okay. Alright, so now let's discuss the operations that we can do in queues, and there are like different varieties or different variations of queue. So for now we are only considering the regular scenario or the regular queue. What exactly the other variations are, we'll discuss in some time. So the first operation is insertion. This is also known as enqueue operation, which says I want to insert an element in the queue. Alright, so let's see the pseudocode of insertion and then check how exactly insertion occurs in constant time complexity. Okay, so we initialize the queue. Queue is initially it will be empty. I am considering it a 0 index queue. So 0 to n minus 1. N is the size of the array. Okay, the size of elements that can be added, the number of elements that can be added in this queue. So initially both head and tail are 0. So what we have done, we have initialized both head and tail with 0. So with a very basic example, taking n as 4. So both head, so I am like denoting head with small h and tail as small t. This is index 0, 1, 2, and 3. Okay, so size of this array or size of this queue is 4, and initially both head and tail are pointing towards 0, the first index. Alright, so now I want to insert, and what enqueue operation is, insert an element x at tail, rear or end of the queue, and generally the end of the queue is denoted by the tail pointer. Okay, so it can be exactly the pointer of the last element or the pointer of the element in at which the place at which you will insert the next incoming element in the queue. Okay, so in this case I am assuming that it is the pointer on which you will add the last element. Okay, the index at which you will add. So again, similar to stack, if the queue is full, in that case you can't add further elements in that queue. So this is the overflow state for the queue. So if tail is equal to n, it will be an overflow. And similarly, when you are trying to delete an element and you like come up at a conclusion that there is no element present in the queue, in that case it will be underflow. So both overflow and underflow is possible in stack and queue. So the first condition is, before adding we'll check for overflow. If queue is full, return it, you can't add any further elements. Or else if the queue is not full, in that case, since we are going with the assumption that tail is the pointer at which you will add the next element, you will straight away add update tail with x. Q.tail would be x. So if I am adding 1, if I add 1, 2, 3, 4, 5 in this queue, let's assume this is the order in which we are adding elements according to this algorithm, this pseudocode. So whenever the first one is encountered, Q.tail would be x. Initially H is 0 and tail is also 0, right? This is what we initialized both head and tail with. So on the first enqueue, q dot tail will be x. So I will add 1 over here, right? And then the tail is incremented by 1. Why? Because whenever the next enqueue operation will occur, in that case, tail should point to the next empty block. So tail is no longer pointing to 0. Tail will be pointing to, this will be the new tail. So tail will get updated to index 1. So the next enqueue should straight away q dot tail equal to the next value that we want to insert in this queue. Okay. So 1 is fine. Then if I want to add 2 in this queue, the algorithm remains the same. We'll check for overflow, and that in this case there is no overflow. So you can add q dot tail. Tail is 1 in this case. So element 2, element x will be added at index 1. So we'll add 2 over here and increment the tail. This tail t will get incremented to 2. Correct? Now if I want to add 3, this is the third insertion or third enqueue. If I want to add 3, no overflow, else part, I can directly add 3 over here and the tail is incremented to 3. Okay, so now let's assume one more enqueue operation to add 4 in this queue. So again, tail is not equal to n. In our case, n is 4. Tail is not equal to 4, tail is 3. So one more element can be added in this queue. So 4 we will add here and this pointer will be incremented to 4. This will be tail. So tail is no longer 3, tail is 4. So now if we try to add the last one, which is 5. I want to add 5, but the value of tail is 4 and n is also 4. What it signifies? It signifies that the queue is full. Queue is full and you no longer can add another element, or the enqueue operation is not possible. So this is an overflow state. This will be an overflow state and will just return saying that it's an overflow. You can't add further elements in this queue. So this is how, while performing this enqueue operation, the only pointer that is required is the tail pointer. So tail will be used whenever the enqueue operation is performed. Okay, and it depends upon implementation to implementation. There can be implementation where you initialize tail with -1 and saying that tail is the pointer, tail is the index of the last enqueued element. It is also possible. In that case, you first increment the tail and then update the queue. That's it. The only difference will be there. But algorithm wise, the data structure remains the same. It is the queue. Okay. So now if I have to ask you, what is the time complexity of insertion? What is the time complexity of enqueue operation in this queue? What it will be? It's just a updation in an array. Like we know the index, just update the element. So it is constant time complexity. Time complexity is big O of 1. Right? So now let's see the next operation, which is deletion, or also known as dequeue operation. So now the head comes into the role. We will check the head and then perform this deletion. Okay, so it removes an element from head or front of the queue. So let's see, let's take the same example. I have a queue where n is 4. I have a queue with n is 4 and there are like few elements. We already know how to update the tail. So let's assume it has 3 elements, 1, 2, 3. Index will be 0, 1, 2, 3, and at this instance head will be at 0. Why? Because like insertion won't change the value of head, and tail will be at index 3. Tail will be pointing to 3. Why? Because there is one place vacant in this queue and one more element can be enqueued in it. Okay, so head is pointing to 0, which is head is pointing to the front of the queue. Okay, so if I want to delete an element, I will use head to identify the position of the element that I need to remove from this queue. So the pseudocode of Dequeue will be, first we'll be checking whether the queue is empty or not. First we'll be checking whether the queue is empty or not. Why? Because if it is empty, then you can't remove an element which is not present in that queue because it's empty. So it is the underflow state. And what is the condition? Whether head is equal to tail or not. In this case, head is 0 and tail is 3. So they are not equal. So no underflow. Elements are present in this queue. So we'll come to the else part, which says take a temporary variable x is equal to q dot head. Why? Because head is the pointer which is pointing to the first element, pointing to the element which is at the start of the queue, right? Which is at the front of the queue. So q dot h, q of h, in this case, it will be 1. Why? Because h is 0. So q of 0 will be 1. So this will take and allocate to x. So now x is 1. And I will update the head. What I will do? I will update the head by 1. So head, now the head will point to index 1. Now the head will point to index 1. And will simply return the value of x. So this one will be return it. Got it? So 1 is the element which was added to the queue first. So this, whenever a dequeue operation will be there, 1 will get removed. Well, 1 will get removed from the queue or returned. So similarly, now if I want to perform one more dequeue, this head will be updated to 1. If I have to perform one more dequeue, we'll check for underflow. Head is 1, tail is 3, so no underflow. Element can be deleted. So the next dequeue operation, again x, a temporary variable, the value will be q of head. The value will be q of head. Head is pointing to 1, so the value of x, second dequeue. This was first dequeue. This was first dequeue. Now if I perform another dequeue operation, now x will be q of head. Head is 1, so it will be q of 1, which is value 2. H will be h plus 1, so head will update to 2. Head will point to index 2 now. This will be head. And return x. So this 2 will be returned. This x, which is 2, will be returned. That's it. This is the second dequeue operation. What if I perform third dequeue operation? In that case, this h will then point to 3. The third dequeue, the queue will be empty. And if I go ahead and perform the fourth dequeue, in that case h and t are equal. So this if will trigger and error would be returned, saying or stating that it's an underflow state and you can't further delete elements. Why? Because the queue is empty. Alright. So now see the code, see the pseudocode of Dequeue, and think what will be the time complexity of the deletion operation or Dequeue operation in the queue. So only two operations, one assignment and one increment. So both are constant, these are straight away, we are reading it from an array, so it will be constant time complexity, and incrementing a pointer. So this Dequeue as well will be big O of 1. The Dequeue operation is also big O of 1, right? Okay. So let's have an example to further improve the understanding of how Enqueue and Dequeue works if these operations are performed in this order which is given in this illustration. Okay. So the initial run, initially head is 0, tail is 0, and let's assume the size of the queue is 3. Let's assume the size of the queue is 3. So it is very important to have a clear understanding of how these pointer will change upon performing these operations. Okay, and like it is very much possible. Question can be framed stating that suppose a blank is given in the code, and based on some initial values, head 0 tail -1, or head -1 tail 0, you can ask to fill line number 5 in the code which is like missing in the first place. In that case, you like don't straight away go and increment head by 1. You have to think based on the initial values or based on the code snippet given. You need to perform the operation given, whether it is DQ or NQ, or it can be anything, and based on that you need to take decision that what will be the missing line of code, given that I want to delete from the front and I want to add the element at the tail of the queue. Okay, don't like go in straight away mark 00 as the answer, or like which is the obvious one, but it will be incorrect in that case. So think and then answer. Yeah, so let's continue. Initially it's empty, n is 3, indices are 0, 1, 2, and head and tail are both pointing to 0. Okay, so next step number 2, NQ10. Let me write head, value of head as 0 and tail as 0 initially. So NQ10, what will it do? We'll see what is the value of tail, and according to our implementation, the tail is the index of the position where we want to add the element. So 10 will be added over here and increment the tail by 1, right? So this is T. Then one more NQ operation again at 20. So 20 will be added, tail will be incremented, and now tail will point to index 2, right? Again NQ operation, same, there is no overflow, one place is like vacant, so 30 can be added and T will be incremented. It is not pointing to anything, so T is now 3, right? So now I want to perform a DQ operation. So whenever we want to delete it from head. We'll see what is the head pointer and then just remove that element. So this DQ will remove 10 and this H will be incremented to index 1. This is 1 and DQ will always return the value. So it will return 10. It will return 10, right? Now step number 4. The first operation is NQ40. So seeing this, the value of T, is it possible to add one more element in this queue? You check the overflow condition again. This is the overflow condition. If tail is equal to n, it's an overflow. In our case, tail is 3 and n is also 3. So both are equal, right? This is the overflow state. So even though there is one position empty which is index 0, so index 0 is not utilized at this point, we can add the value at index 0, but since we are discussing the regular queues, it will be an overflow state and this NQ won't be possible. It's an overflow. It will be an overflow. And same holds for this NQ. This will be an overflow. Both of them will result into overflows. So H won't get impacted and T will also won't get impacted. Why? Because T is equal to N, and whenever this condition arrives, it's overload, the queue is full. But like in the actual scenario, there is a position empty in this queue. Now step number 5, you DQ again. Possible, right? H is pointing to index 1 and is not equal to the tail. So it tells us that you can delete an element So this 20 will be returned, this h will be updated to index 3, index 2, the third place in this queue, and this will return 20. This will return 20. Now at step number 6, another enqueue. Is it possible? No, right? T is equal to n, so this will also be an overflow state. Alright, so this is how the regular queue will work. So based on these, so this overflow can be avoided using a slight modification in the regular queues. So we have already, there is space available in this queue, but since the implementation of regular queue is not allowing us to insert elements, even though there is space available once t exceeds n-1 index. Once t exceeds n-1 index, you can't further add elements in a regular queue, no matter you have performed few dequeue operations which have provided a vacant space at the front, right? So this is the disadvantage of the regular queue. So let's see circular queues. So why we exactly study circular queue? Because there is a drawback with the regular queue, which is once the tail reaches the end, it wastes the space, even though the space is present in the start of the queue or the front of the queue, like before the front. When the tail reaches the end, the space will get wasted, and you no longer can add the element in the queue, and it will always throw the overflow error. So here comes circular queue to rescue this wastage of space. What exactly it is? It is also a data structure which follows FIFO principle, first in first out. It is a queue. The only difference is the tail connects the last position back to the first position to form a circle. That's why the name circular queue. Whenever the tail exceeds the last position, we update it in such a manner that it creates an abstraction that it is connected in form of a circle. So let's see how exactly the space gets wasted and how circular queues will remove this issue with the regular queue. Let's assume n is 4 and the index is 0, 1, 2 and 3. Both head and tail initially will point to 0 index, right? And now let's keep on adding the elements. I have added one, Enqueue1. So tail will update to this. This is head, this is tail. Initially 0, 0. After first enqueue, tail is 1. Now I have added 2. Tail will be 2. Now I have added 3. Tail will be 3. Tail will be 3. Index. Now what if I remove an element? I perform a dequeue operation. Remove it. Update the head to index 1. Okay, at this instance, head is pointing to index 1 and tail is pointing to index 3. Okay, and there are two positions empty in this queue, which is at index 0 and index 3. Now let's add one more element 4 in this. So the tail will get updated to index 4, which is the value of n. This is an overflow. Overflow after this addition of 4. You can't further add any element even though index 0 is empty. Okay. So regular queue this is the disadvantage of regular queue. This is what the wastage of space means. Alright. But in circular queue, what we will do? Rather than keeping the value of t as 4, once the dead end is reached, or we are out of memory or this size is reached, we will ensure that t should not get updated to 4. In fact, t should point to the starting, which is head, which is index 0. So this creates an abstraction, or it gives an impression that after t is 3, it will update to 0 in such a way that the queue is in circular fashion. Alright, so how we'll do? Let's see. The first operation in the circular queue is insertion Enqueue at the tail of the queue, and here tail is no longer will point to the end of the queue. It is, the queue is in a circular fashion, so there can be a possibility that the index of tail can be less than the index of head. It is very much possible in circular queues. Okay, it's say x, index x and index y, and it is possible that x is less than y. It is possible. Okay, but it is not possible in regular queues. So let's see the pseudocode for the circular queue Enqueue operation. So initialization is same. Head and tail both are initialized with 0 given an array of size n, right? So the only difference here is in line number 1 and line number 5. Okay, so the overflow will be a state when tail plus 1 mod of n. This is modulus operation, remainder operation. Mod of n is equal to head, which is an overflow. We'll see it in some time. And the updation. So this queue dot tail will be x. We'll add the element in the queue, and tail will not update. In the regular queue, we just update t as t plus 1. We just increment the tail by 1. In this case, we won't increment it. We will increment it by 1 and then take mod with n, which is the size of the array. So let's see an example of how this modulus will ensure that after exceeding the size, tail should point to the start, or it gives a circular impression whenever t is 4. Let's assume n as 4 and take the same example that we saw in the previous case. We have h and we have t, and we are performing Enqueue operation over here. Initialized both with 0, size is 4, so h will be 0, tail will also be 0. Okay, and I have enqueued 3 elements. This is h and this is t. I have added 1, index is 0, 1, 2 and 3. I have added 1, then 2, then 3 and 4. So initially t will point to index 0, then t will point to 1, then it will point to this, then this, and after the fourth addition, so at this point, let's assume we have only added 3 elements, 1, 2, 3, Enqueue1, Enqueue2, Enqueue3. So till now we have successfully added 3 elements, or 3 Enqueue operation has been done in this queue. Let me write it down over here. The first was Enqueue1, then Enqueue2, then Enqueue3, and now we want to perform one more Enqueue, which is Enqueue4. So my question is, based on what the if condition for the overflow and the current implementation or current pseudocode of the circular queue is, and the initial values 0 and 0, is this operation 4 possible? Just like pause the video over here and think whether this fourth Enqueue, can we insert one more element in this queue? The answer is no. Why? Because of this termination condition. It is an overflow state. So based on this implementation, where if the overflow state is tail plus 1% n is equal to head. So tail is 3 in this case. In this case now tail is 3. So when we go and try to perform this operation, which is step number 4, fourth insertion in this queue. So tail is 3, 3 plus 1 will give me 4. Percent 4 with n will give me 0, and this is exactly equal to head. Why? Because head is 0. So this is overflow. This is overflow, and this fourth Enqueue, this operation, you can't perform. Correct? So based on the initial values, head 0 and tail 0, and this overflow condition, a circular queue of size n will be having maximum n minus 1, which is 3 elements. It can only have maximum 3 elements. So now I have a homework for you. So what should be my overflow condition and the initial states of head and tail to ensure that this circular queue should have 4 elements, and in this implementation will always waste one space, and you can't add more than n minus 1 elements if you are implementing a circular queue using this overflow condition and the value of head and tail as 0 0. So since in the regular queue implementation we have taken head and tail as 0, so that's why I have kept it same, but this implementation will you can't add the nth element in the queue, only n minus 1 maximum elements. Alright, so now let's see the dequeue operation, and then we'll see a combination of both of them illustration to understand how these heads and tails are incremented or changed in circular queues. So next one is dequeue, which is removes an element from the head of the queue, which is the pointer, h pointer that we are taking in these illustrations. So the termination condition of underflow, when the queue will be empty, when head is equal to tail. When head is equal to tail, no further elements can be removed from the queue. So let's have n as 4 to understand how this operation works. Okay, and I am considering the same set of operation, 3 enqueues. The 4th enqueue won't be possible, then we need to perform some dequeues in order to remove a space so that some more elements can be added, right? So initially h and t are both pointing to 0. So these are the operations. The first is Enqueue1, Enqueue2, Enqueue3, Enqueue4. We already know that it will be an overflow. Then Dequeue. Then again try to add 4. Okay. So the value of h will be 0, t will be 0 initially, right? So overflow, what will be the underflow state when head is equal to tail? Else you assign x as head, the value which is present at the index head, and then increment the head and take mod with n, correct? And then return that x. That's it, right? So in these operations, so we are starting with addition of 1. So can we add 1? Answer is yes, we can. 1 will be added here and tail will be incremented to 1. This will be t. Can we add 2? We can. This will be t. Okay. 1 will be updated to 2. So this is also possible. Can you perform the third operation, which is adding 3 to this circular queue? The answer is yes, we can. 3 will be added over here. Now t will point to the index number 3, the last position of this circular queue. Correct? So now if we try to add one more element, 4. So we won't be able to. Why? Because tail plus 1, 3 plus 1 %n is equal to head. So this is not possible. This is not possible. Okay. So t will remain as 3. Now let's try to have a dequeue operation. So in a dequeue operation, we'll check for underflow. Is head equal to tail? Head is 3, head is 0, tail is 3. Are they equal? No, right? So dequeue can be performed. We can have a dequeue. So x will be returned, q of 0 will be returned. This will be returned, will be removed, and head will get updated to index 1. This will update to 1. So 1% n, 1 mod 4 would be 1 only. So this modulus we won't see the impact of mod of n. So this is possible. This is possible. Now the last Enqueue. So now let's see. So h is now 1 and tail is 3 and we are trying to perform Enqueue operation. So what is the overflow state? The condition is t plus 1 mod n. If this is equal to h, then it's a overflow. So let's see whether this is an overflow state or not. So in a regular queue, this would be an overflow state, right? You add one more element and then you try to add one more, it will be an overflow. But in this case, since head is shifted to index number 1, there are two places empty, and we have already, like I have already told you, that this implementation will always ensure that maximum n-1 elements can be put inside the circular queue. For now, there are like two elements, n-2 elements are there, two places are empty, so one will always be empty, but you can further add one more element and it won't be an overflow because t is 3. So 3 plus 1 would be 4, percent 4 mod of n will be 0. Is this 0 equal to 1? No, right? So it is not an overflow. It is not an overflow. This condition is false. So else we will add the element x to the tail index and will increment the tail and take mod of n. So this operation will update tail as tail plus 1 mod n. It will be 3 plus 1 4, percent 4, which is 0. So tail will be updated to 0 and this 4 will be added to here. Tail will be updated to 0. Got it? So this is a circular, this is giving a circular impression. Your tail was pointing to 3. Now it has started again from index 0. Okay. Now if you try to have one more Enqueue, it will be an overflow. Why? Because there are already 3 elements, n-1 elements in the circular queue, so it will be an overflow. But if there are some delete operations, in that case you can successfully add. Okay, so let's try to have few more dequeues until the underflow state is reached. So we have 3 elements, so 3 dequeues will be successfully possible. DQ1, DQ2, DQ3, and then finally the last DQ. Let's see if these operations are possible or not. So step number 7. So this is the current state. Index 0 is empty. You have 1, 3 and 4, the state of the queue, right? And you try to perform a DQ operation. So it will check whether head is equal to tail. Head is 1 and tail is 0. So they are not equal, so it is not an underflow. So you will return x and update the tail by 1 mod n. Okay. So this one will be updated to 2, correct? And this 2 will be popped out. This will be popped out. Okay. And this is the new head. Correct? Tail is like still pointing towards index 0. Head is pointing towards index 2. So this is possible. This is 7th is possible. Now try to have one more DQ. Head is pointing towards 3. 3 is not equal to 0. No underflow. X would be Q of 3. X will be, so this 3 will be returned. Head will point to 4. This will incremented by 1 mod n. It's less than n, so mod won't have an impact, and step number 8 is also possible, right? Now your head is pointing towards 3, which is this, the last index. We have one more DQ operation. The underflow state, head is equal to tail. Head is 3, so 3 not equal to 0, so no underflow. So you can remove the element from this circular queue. So this 3 will be incremented to 3 plus 1. 3 plus 1 mod 4, which is 0. this 3 will updated to 0. This 3 will get updated to 0 and this element will be returned, and this will be your new H. At this point the queue is empty, and whenever the queue is empty, you try to perform the last dequeue operation, which is step number 10. This is not possible. This is not possible. You can't remove an element. Why? Because head is equal to tail. So both head and tail, once they reach beyond index 3, you will take a mod with n to ensure that both head and tail should always lie between 0 to 3. So therefore this will be an underflow state and you can't have further dequeue operations, but enqueue is possible. Both this is the reset state of this queue. This is the state in which T and head, both T and head are pointing towards 0 0 and the queue is empty. So you can, n is 4, so you can straight away go and add 3 more elements in this circular queue. Alright, so in this way you won't face the wastage of the space even though if it was present, right? The only drawback with this implementation is, based on these conditions, head is equal to tail plus 1 %n is equal to head for overflow and underflow and the initial state. There is always like one space will get always wasted, but yeah, this can be saved using either by one more element, one more variable which keeps a track of how many elements are present currently in this queue, or by tweaking the initial states and these conditions. Okay, so take it as an homework and try to come up with a code snippet or a pseudo code which ensures that queue at max can have n elements if the size of the data structure is n. Okay, but the overall idea remains the same. The crux of having a circular queue is whenever the index reaches beyond the last index n-1 for both h and t, it should straight away point to the starting one, right? And yeah, for circular queue as well, this enqueue operation is of big O of 1 time complexity. It's just an update and incrementing the pointer, and same holds for dequeue. This is also having time complexity of big O of 1, right? So now let's have one more dry run over what we discussed till now. So the size, the head is 0 initially, tail is also 0, and size is 5. So maximum it can have, if it's a circular queue, in this case it is, so maximum it can have n-1 elements, right? But yeah, there might be a question in which a circular queue would have exactly n elements, but the pseudocode and the logic will be slightly different. Okay, so just take care in these scenarios. Yeah, so step number 2, enqueue 10, enqueue 20, enqueue 30 and enqueue 40. So I won't be going step by step. I will just take the queue, of size 5, so it can have maximum 4 elements, right? So we are inserting, we are adding 4, 10, 20, 30 and 40. So initially h is 0 and tail is also, head and tail both are 0. So we will add 10 over here, 20, 30, 40. This 4 addition or these 4 enqueues will update tail by 4, right? So tail is pointing towards this after step number 1 and head is pointing towards 0. Okay, because there was no dequeue operation. Step number 3, dequeue, remove one element. So this will be removed and h will be updated to this one, right? Now perform enqueue 50 and enqueue 60. So no worries till step number 3, all operations will go smoothly. So step number 4, enqueue 50. So first we'll be checking for the overflow condition. T is 4. So what was the condition? T plus 1% n. If it is equal to H, then overflow. If it is equal to H, then overflow. And when H is equal to T, it's an underflow. So step number 4, the first operation we need to have like Enqueue 50. Okay, so first before every Enqueue or like before every Dequeue, just check for the overflow and underflow conditions. So Enqueue 50, when we try to do Enqueue 50, at this instance T is 4. Okay, so T plus 1 would be 5. T plus 1 will be 5. T plus 1 mod n. So 5 mod 5 is 0. So is it equal to H? We have H as 1. So it is not equal to H. It is not equal to H. So no overflow. So we can successfully add one more element in this queue, which is 50 in our case. So we will add 50 and T no longer point to this. T will be 0. T will be 0. Why? Because we update after insertion, we update T as T plus 1 mod n. Okay. So at this point, T is pointing towards 0 and H is pointing towards index 1. Okay, and there is one like position available. So we already have like filled 4 elements. So according to like our implementation, we can't add like further. And this Enqueue, when we try to have one more Enqueue, this will be an overflow. Why? Because size is already 4. Right? This condition will return true and it will be an overflow. Why? Because T plus 1 will be 1. Percent n, again it will remain 1 and this is equal to H. T plus 1 mod n will be equal to H. So it's an overflow. So here you can't perform this operation. Step number 4, second Enqueue. Now let's see step number 5. Again we try to have an Enqueue operation. We can't perform. Again it will be overflow. Logic remains the same. Step number 6, it's a Dequeue. Possible? You check for underflow. H is equal to 0, H is equal to 1 and T is equal to 0. So it is not a underflow. They are not equal. So you can remove. And H will point to 2. This will update it to 2. T will remain 0. Okay. So this is possible. Step number 6, you try adding 80 and then try adding 90. So let's see, can we do it? Check for overflow. T is 0. So 0 plus 1. 0 plus 1 mod n will be 1. Is it equal to 2? The answer is no. So no overflow condition. You can add at 0. And what will be adding? Will be adding 80. So this will contain 80 and T will be updated to 1 second, let me move it to create a space. Yeah, T will be pointing towards 1 now. T will be pointing towards 1. At this instance, the value of tail index is 1 and head is 2. And so this will be possible. Now one more Enqueue. Is it possible? The answer is no. It will be an overflow. Okay. So based on like our logic, it can have maximum 4 n minus 1 elements, but the circular behavior will be there. Why? Because of the increment of T by T plus 1% n and the increment of H by H plus 1% n. Alright. So here is like what circular queue can bring up on the table, and like it removes the disadvantages, it eliminates the disadvantages that we get using a regular queue, right? So now let's see some more variations of the queues. So till now we have discussed regular queues, circular queues. So like there are two more variation in queue. The first one is Dequeue, DEQUE, pronounced as Dequeue. Okay, so Dequeue is basically a special type of queue which ensures addition and deletion, which ensures insertion and deletion at both the ends. at both the end. Okay. So this ensures addition and deletion at both the ends. And like this deck can be implemented only using a linked list if we want a more optimized implementation of this deck. Suppose this is the existing n as 4, having 4 elements. So at both the places, this is end, you can add or delete, and at head as well you can add or delete. Okay, it will be more clear when we discuss the doubly linked list. It is generally implemented using a doubly linked list. So, but for now, you can think of it as a variation of queue, which which allows us to perform insertion in front, insert rear, delete front, delete rear, and get the value of head, get the value of tail, right? So for now, this is sufficient, and we'll revisit the decks when we discuss the doubly linked list. Okay. So here is one more variation of queues, which is known as priority queue. Okay, so as the name suggests, there is certain priority associated with the elements that we're gonna be adding in this queue, and the addition won't be a sequential that was in the case with regular or circular queues. So you can think of as an analogy. So like, what if there is an hospital that have only two departments, first OPD and second for to treat emergency patients, and there are certain patients like sitting in the OPD department, and what if an emergency patient comes up? So the priority of the hospital is to cater that emergency patient, no matter like how many number of OPD patients are already present, right? So same holds for priority queue. So when an element, when we add an element which is having a higher priority with the elements which are already present in that queue, then the next dequeue operation or the next delete operation would be the element which is having the highest priority, right? So we won't be we won't be discussing this briefly over here. Why? Because the efficient implementation of priority queues is done by heaps. So after discussing heaps, we'll revisit again priority queue. But at this point, I am just covering how exactly this works. Okay. So special type of queue where each element will be having a priority. Each element will be having a priority. Okay, and it is of two types, max priority or min priority. The two variation. The first is max priority. It means that the element that will be deleted will be having the highest priority. So highest priority element will be deleted or catered. And the second is min priority. It means the element having the lowest number of priority will be deleted first. So lowest priority element will be deleted. Okay, and the operations are insert, and in each insert you will send the element X that you need to add with the priority. Okay, so the element will get added based on what is the priority of that element and the elements present in the queue. Okay, and then delete. So remove element with either highest or lowest priority based on which priority queue you have implemented. Either it is a max priority or a min priority. We'll see an example to have a dry run how exactly this works. Okay, and these are like empties for the regular overflow and underflow checks of this priority queue. So first, let's see how this min priority works. Okay, as the name suggests, so min priority. So the least number of priority would be the one which will be deleting. Okay, so n is say too large, So there won't be any overflow state. Initially the queue is empty. Initially the queue is empty. And there is no concept of head or tail when it comes to priority queue. And like the efficient implementation is done by heaps, so head and tails are not required. But I'm just like giving you a dry run of how exactly it works. So the first element, the step number 1, like initialize a queue empty. Then step number 2, insert a element 10 with priority 3. Insert a element, and we are implementing min priority. Okay, so the first element that will be inserted in this empty queue will be 10 with priority 3. So it will be a tuple that will be inserted having two values, x and its priority. Okay, then you will insert 20 with priority 1. So now the next element that will be inserting would be 20 with value as 1. So again there are two variations in which this is implemented. The first way is whenever you insert an element, the first way is whenever you insert an element, immediately rearrange them in such a way that they are in the order of the priority in which you have implemented. In this case it's a min priority, so at the time of insertion you insert this 20,1 at its correct position in such a way that this priority queue always remain in increasing order of priority. Okay, this is way number 1 in which you can implement. And the advantage of this implementation is you just have to pop, or you just have to remove the first element to get the element having the least priority, because it will always hold the first position. Why? Because the priorities are increasing in order. So the first way is to always maintain the priority. Always okay. So to do this, to ensure that priority is always maintained, every insertion should, the insertion won't be in sequential manner. So insertion won't be in sequential, insertion will be in such a way that least priority should always be on the left hand side. Okay, which is increasing order of priority. Okay, so at this point when you try to insert an element value 20 and priority 1 in a min priority queue, so will this fill the order? The answer is no. The correct order will be this 20,1 and the first one 10,3. So every insertion will ensure that it should get inserted, the new element should get inserted in such a way that the increasing order of priority should always maintained. So this is the first way. So if you are like having a sequential, if you are using an array to implement a priority queue, so in worst case scenario, there can be a case when the last element, the n minus nth element that you want to add in this priority queue might have the least priority. In that case, you have to shift all the elements towards its right and you have to add the one which you want to insert having the least priority at the start, so that the deletion should always pick that one. Okay, so worst case of complexity in this case would be, for insertion, would be big O of n, and this is only for the case when you are using an array to implement or a sequential implement, right? But like using heaps, this can be reduced to log n. This can be reduced to big O of log n using heaps. This is for insertion, right? Okay, so at this point, after step 3, so let me write the queue here as well, what the value of queue will be. So the queue will be after step 2, 10,3, only one element. After this, it will be 20,1 and 10,3. And deletion are happening in such a way that you will always go and remove the first element. Why? Because it will be the least priority element in the queue, because you are always maintaining the increasing order of priority. Step 3, insert 30 with priority 2. Okay, so already we have two elements with priority 1 and 3 in this queue. So the next element will get inserted exactly in the middle position. So the new updated value of the queue will be 21, then 32, and finally 10 with priority 3. This will be the value of queue after step number 4. Right? Now it's a delete operation. So what delete will do? Delete will since every insert we are maintaining the order of priority, delete will simply go and remove the first element. Delete will go and remove the first element. After deletion, this will be removed. The queue would be having 30, 2 and 10, 3. Okay, why? Because we are maintaining a minimum priority queue, a min priority. What if it was a max priority? In that case, the deletion will always remove the element having the highest priority. Okay, so in that case, it will be in reverse order, right? Every insert should ensure that the decreasing order of priority should be maintained, and the first element in that case will be the element having the highest priority. So just remove that. That's it. We'll see it in the next example. Okay. So after step 4, step 5, this will be the queue. After step 6, insert 40 with priority 0. So 0 is the least which is present or which is already present in the stack in this queue. So the updated value of queue will be 40, 0 in the start. Then you have 32, 30 having priority 2 and 10 with priority 3. Okay. And then one more insertion with priority 4. Element 50 will get added at the last. Why? Because priority 4 is the highest among all of them. So it will be 40, then 30 and 2, 10 with priority 3 and 50 with priority 4. Okay, and at this point we are not discussing the implementation or the logic, how you implement it. We are just discussing the working of a priority queue. Okay, we'll revisit the logic once we complete heaps. Then it's a delete. So delete will simply go and remove the element having the least priority in a min priority queue. So after delete, 40, 0 will be returned and the queue would be 30, 2, 10, 3 and 50, 4. And step number 9, insert 70 with priority 1. So priority 1 would be the least among all three. So it will be added at the first position. The queue will be 70, 1, then 10, 3, no, 30, 2, then 10, 3, and finally 50 and 4. Okay, so this is slightly different from the regular or the circular queue, where the insertions are always like addition is always done at the tail and deletion is always done from the head. In this case, the deletion is done from the head. Like why? Because we are ensuring that always the increasing order, decreasing order of priority should be maintained. The second implementation can be slightly different. You always add the element at the end, but in the deletion, you go through, you iterate over all the elements and then choose the index having the least priority in case of a min queue, and then remove it from the queue. So like but like the idea remains the same. In this case, you are always maintaining the increasing order and then removing the first element. The second scenario would be always add at the end and then iterate when you want to delete to find the element having the least priority. Okay, so you can write it the second way to implement it. The second way can be always insert at the tail but the drawback will be deleting. While deleting, you have to find, iterate over all elements to find least priority one. To find the least priority one. Alright, and in this case, if you are going with the way one of implementing, insertion would be big of n or log of or big of log n based on like how you are implementing, and deletion will be constant. Like in case of log n, deletion will be constant, but in that case you again have to rearrange the heap. So like I'm not getting into heap right now. We'll discuss later. But yeah, for now, either way you can implement a priority queue, right? So now let's see how the scenario will change when you are trying to implement a max priority based on, like, the example is the same. The first step is to have a queue empty. The second is to insert 10 and 3. So at this point, the queue will be having only one element, 10, and I am going with way number 1, which is every insertion is in such a way that the element is added at the correct place based on decreasing priority. Why? Because I want to cater the max priority first. Okay, now insert again with priority 1. With priority 1, this priority 1 would be an element with a lesser priority compared to priority 3. Why? I am implementing max priority. So the queue will be 10, 3, then 20, 1. This will be the value of queue after this insertion. Then you insert again 30 with priority 2. So you will add it exactly at this point. 10 and 3 having highest priority, then 30 with priority 2, and then 20 with priority 1. Okay, now you delete. Delete is just simply removing the first one. Why? Because we are already maintaining the order of priority. So we will have 32 and 20, 1 in the queue, and this will return 10, 3. 10, 3 will be returned. Next, insert 40 with priority 0. 0 priority is least among all of them, so it will be added at the end. Values will be 30, 2, 20, 1, and 40, 0. Alright, then one more insertion with priority 4. 4 is highest among all of them, so it will be added at the start. So then 50 with priority 4 will be the first, then 30 with priority 2, then 20 with priority 1, and finally 40 with priority 0, which is the least among all of them. Now it's a delete. Delete will simply remove the first one and return the updated queue. Updated priority queue would be 30 with priority 2, 20 with priority 1, and finally 40 with priority 0. Now if we want to add 70, the last, with priority as 1. So like there is a tie. Why? Because there is already one element present in the queue having the same priority. In that case, you can cater anyone. It will depend upon implementation to implementation whether you want the newly added element towards the extreme left, which ensure that it should be removed first if the priorities are same, or it can be at the end. So both are correct. As long as it is not affecting the priority, it's correct. Okay. So the last addition will be like this. It will be 30 with 2, then 20 with 1, 70 with 1, and 40 with 0. 70 with 1 and 40 with priority 0. Okay, so this is the order in which you will remove the elements, and we always ensure that addition maintains the priority. The second way, you just add at the end, and deletion, while deleting, go through all of them and remove the one with maximum priority. Okay, so this is how the priority queues are generated and maintained, right? We'll go through the code and other aspects of complexities and priority queues later on. So now let's see few of the applications of queue. Okay, so when we were discussing stacks, so there was a point of like that stacks are used in optimizing the code, where I gave an example of like CPU scheduling, but it was not stack, it's in fact queue. So queue plays a vital role when it comes to CPU scheduling. So regular queue is used in FCFS, first come first serve CPU scheduling algorithm. You will read about these algorithms in OS. So generally regular queues are used in this. Then if you have a printer, you can give print commands to a printer that also uses a queue, which ensure that the command which came first should be the one the printer should receive and act upon. Then BFS. So we'll briefly discuss breadth first search in graphs that also use the regular queue to implement the breadth first order of traversing the nodes that are present in that graph. Then comes circular queue. So there is another scheduling algorithm called round robin. So this round robin algorithm is like use circular queue to have this round robin fashion in such a way that if you have four processes, so CPU should get the all the four processes should get the same amount of execution time by the CPU in a round robin fashion. So it's process 1 that will be catered first for X amount of time, then it will be process 2 for again X amount of time, P3 again X amount of time, P4 again X amount of time. Then after P4 is done, after this X is over, again the control goes to P1. This is the round robin fashion. So it is implemented using a circular queue. Okay, then DEC. So sliding window problem, palindrome checking. These are like problems which uses doubly linked list or DEC. So like both the words will be interchangeably used in the course. This is implemented using doubly linked list. We'll see it in linked list. Okay, and then finally the priority queue. So there's one more scheduling algorithm based on the priority. So what if there is another process? So like the queue already have four processes, and every process will be having a priority associated with it. Okay, let's call it 1, 2, 3, 4 the priority. Okay, and the CPU is giving the time to process all of them one by one based on their priority. Then what if emergency process or the process which requires the CPU, like which requires the attention having like highest priority arrives, P5 with priority 0. So in that case, this will be the process that should be executed first, no matter how many processes are already in the queue. Okay, so priority queue and Dijkstra's shortest path algorithm like also uses priority queue in order to find the shortest path between 2 points or 2 nodes in a graph. Alright, so let's see the demo of queues, how we can implement it. So now let's see how a queue can be implemented in Python. So there are two ways to implement a queue in Python. First, which we will be discussing now, would be using lists, right? So we have seen how using a list a stack can be implemented, right? Similarly, we can use list to implement a queue in Python, but there is a small drawback when it comes to using list for implementing a queue. We'll see it. And another way is by using DAX. Okay, so deck is basically a predefined library in collections that can be used in order to implement a queue, right? So we have collections which is a toolkit of different libraries in Python, and among which deck is one of them. which is basically inbuilt implementation of a doubly linked list. So like right now I won't be discussing deck because we will cover linked list and doubly linked list in the next module. Over there we will see how a deck can be used to implement a queue, which will be a more efficient way, which will be a more efficient way when a queue is implemented compared to lists, right? And similarly we have there are multiple other libraries apart from decks in the toolkit called as collection. So you will be having counters, you will be having default dictionary, we have this ordered dictionary where the order of the keys are maintained in which you are adding them, and so on. Okay, so out of which deck will be useful when we implement doubly linked list, right? So for now let's see how lists can be used to implement a queue. Okay, so again the idea remains the same. Let me initialize a empty list with the name as queue, and we have this enqueue and dequeue operations, right? We have this enqueue operation which is adding the element at the end, right, or tail. So enqueuing is similar to having the append operation. Enqueue is similar to having an append operation at the end. Why? Because you can think of a queue as a list in which this is the end or rear part and this is front, right? So initially the queue is empty, so any element that you will be adding in the queue would be placed in the front, right? So let's assume we are appending 3 elements, which is the code will be like this: append say 10, then append 20, and finally append 30, right? So this will be the end of the queue, and the elements will be added by like from the end and will be removed from the front. So after these 3 operations the queue will look like this: we will have 10, then we will have 20, and finally we will have 30, right? And now the first dequeue operation will remove the element which was added first, right? Which is, that's why it's called first in first out data structure. The element which was added first will be the one to leave the queue first, right? So the dequeue operation will get rid of this 10 first, then it will remove 20, and so on, right? So we will be removing the values present or the elements present in the list from the front and add it from the rear part, right? Okay, so appending 10, then add let's say 20, then 30. So let us see, right? So there are 3 elements. First we have added 10, then we have added 20, then we have added 30, right? So now let's remove few of them. So if it was a stack, then this operation would always remove the last element that was added in the list. This operation will remove 30, but this pop function, which is an inbuilt function of list, also takes an argument. You can call this pop function either by not passing anything, which is indicating this to remove the most recently added element from the list. But if you pass a index, in this case say 0, it will always remove from the front. So this will give you 10. And now if you try to print the list, the remaining elements of the queue, it will be 20 and 30. So pop can take an argument. So passing 0 will always remove the first element in the queue, which is the ideal candidate for the dequeue operation, right? So this is how. Again, the second pop will remove the next element which is present in the front. First 10 was removed, then 20 got removed. If you print the queue again, there will be only one element left, which is 30, right? So this is how you will perform the dequeue operation. Dequeue, so remove the element from front. But why this is not an efficient way to implement queues in Python? Because this is not a constant time operation. This is, if you are removing, or like if we are implementing the dequeue operation using this method via list, removing the first element from the list, it is in fact a big O of n operation. What it does is it removes the first element and then it shifts all the remaining element towards its left, so that the immediate next becomes the new first element, which is having index 0, and so on. So due to this time complexity, the linear time complexity, generally we try to avoid implementing a queue using a list. So then the next method that we have is using deques. Okay, this we will cover after discussing doubly linked list, right? So this is how queues are implemented, either by list or by deque. Deque we'll see later, right? Okay.